In pre-calc, the things that we did learn to do, whether you remember it or not, is plot points in the polar form r comma theta. We did do some graphing of polar curves, but we did not do a ton without calculators because we did not have the time to do them. We did some basic circles. We looked at limacons, cardioids, and roses on our calculator, but we did not have time to do those in terms of like graphing them by hand. We will look at that today, okay? We did do converting points from rectangular to polar and vice versa, and we did do equations from rectangular to polar and vice versa, okay? Things we need to know in BC calculus. We need to be able to graph a lot of these polar curves by hand. Some of them will be calculators, some of them will be not. Definitely, we will need to be able to graph the circle equations by hand. They are very quick and simple, but you're going to need to know how to do that. We are going to do derivatives of polar functions next class. And then one of the big things with polar is finding the area of a polar region. So you know how we've done area under curves the whole way through? It's been like the integral from A to B, and it's always from left to right under a curve down to the x-axis, right? Polar gets a little bit different because the whole polar graph is circular. It's a rotational thing. So when we find area within a polar curve, you are going to not be thinking boundaries of A to B as left to right. We're going to be thinking in terms of rotation, like the unit circle. Okay, so we really need to get down what the graph looks like and how to graph these in the circular format before we can find area in curves. So real quick, review of sine, cosine, tangent stuff. Do we remember our chart? Yep, sine starts at 0 and goes out to 1. I think it's really funny that there's degrees on here considering we've never used degrees. What's the corresponding radian to 30? Pi over 6, and then pi over 4, pi over, and pi over 2. Good. Cosine was sine reversed. And then how did we find our tangents?
You divide.
Divide. So I've got 0, 1 over root 3, 1, root 3, and undefined. Underneath this, we are going to write down a couple formulas that we talked about that, again, we probably don't remember from last year on our quick survey of polar graphing, but I'm going to remind you of at this moment. We talked about the x component was equal to the radius times the cosine of the angle. This was kind of your first look at parametric stuff, but we didn't talk about it that way in polar graphing when we converted between x coordinates and y coordinates. The y component was equal to r times the sine of the theta. If you were converting between rectangular and polar, you could find the radius by doing the square root of x squared plus y squared. What does that remind us of that we've just been talking about? Pythagorean theorem, magnitude. We found the angle by doing the inverse tangent of y over x. And then one other formula we worked with was x squared plus y squared equals r squared, which is just the equation of a circle. These are basic formulas that will help you in polar when we're converting between different things, okay? All right, so quick review of how to do polar points and basic polar graphs on the back. So review with me, graphing polar coordinates. This was r comma theta. So remember when we graphed these points in pre-calc, we started by rotating to the angle first, and then using the radius to go out along that angle. What did it mean for us if the radius was negative? You went backwards. So for the first one, we rotate to pi over 4. We do not go out towards pi over 4 because that would be a positive radius. What do we do with the negative 1? We go backwards along the same line, which means this first point, negative 1, pi over 4, would actually be right there. I'm going to call that point A. We did that at the end of pre-calc, and we took a group test over it. Yep. I'll show you my pre-calc binder and make you remember. All right. So the second point, what if we have a negative angle? What does that mean we do?
You rotate the other way.
Rotate backwards. So backwards 5 pi over 6 would put me at 7 pi over 6. And then a positive radius along that line would be 1, 2, 3, 4 out here. We'll call that point B. What about a negative radius and negative angle? Backwards 3 pi over 4. Okay, so if I rotate backwards 3 pi over 4, I land at 5 pi over 4, and then a negative radius takes me back into the first quadrant, yes? So that point, we'll call it C, ends up being 3 out along the line pi over 4, yes? And finally, a positive positive is pretty normal, right? Positive positive would take me, rotate around to 7 pi over 6, and then out along 7 pi over 6, out 2, which would put that last point, I'll call it point D, right there. All right, so for conversion, we use our basic coordinate formulas that we did on the last page. If you are changing to polar, you are going to be using your formula r equals square root of x squared plus y squared, and theta equals the inverse tangent of y over x. Okay? If you are changing the opposite way, we'll talk about those in a minute. Okay? And you can also use the formula x squared plus y squared equals r squared. Those are all changing to polar formulas. Okay? So if I have a point that I want to change to a polar point, I have an x, I have a y, I need to change it to an r comma theta. We're going to talk about that. Yep. You most likely, when you switch to a polar point, won't make a negative r. We will change the angle rather than that. That's easier to do. So first, I would find my r by doing the square root of x squared plus y squared. This is going to give me 1 plus 3. Square root of 4 is just 2. Yeah? I am typically going to keep my r positive. There are about 4 or more ways to write every single point in polar. If you're converting, you don't need to make this more complicated on yourself. Okay? Leave your r positive. We're going to deal with the angle here in a minute. Okay? The angle will get you to the right spot. So to find my theta, I do the inverse tangent of my y over my x. Since I'm dividing by -1, this is really asking me the question, where is my tangent equal to -√3? This is where our chart comes back into play. In the chart, the tangent is equal to √3 at what reference angle?
2 pi over 3.
Flip back a page. Pi over 3 is the reference angle. Tangent is negative in 2 places.
2 pi over.
That is one. What's the other one? 5 pi over 3. You have to decide which one is the right answer.
If x is negative and y is positive, then it's
If x is negative and y is positive, what quadrant are we in?
2 pi over 3.
2, which means my angle is 2 pi over 3. You've got to choose the right angle for where your point is.
Wait, so how's the 2 pi over 3?
So if I'm given an entire equation, first off, do we recognize that kind of equation? Yeah, that's a circle with what radius? 3. You have a couple conversion formulas here that you could use. The easiest one for this one is the top one, because you have an x squared plus y squared. According to that conversion formula, x squared plus y squared is the same as r squared. So you can then solve for r. What is r going to equal? 3. And we're not going to write it as plus or minus 3 because think about it. We just did things with negative radius. If I did a positive radius of 3 at every angle, it goes out 3. What if I did a negative angle or a negative radius? It's the same thing, right? It just gives you a circle with a radius of 3. Converting the opposite way, we will use our other formulas.
Is that all we would write? Is just R3?
Mm-hmm. R equals 3 is a circle with a radius of 3. That is what a polar graph of a circle looks like.
So we don't need a theta?
No, you don't. So if there is no theta, that means it happens at every theta. So your radius is 3 at every theta the whole way around, which gives you a circle. Okay? Because if there is no theta given on that one, that means it happens at every theta. So that means a radius of 3 at every value of theta, which then takes you out 3 the whole way around at every angle, which gives you a circle.
Oh, how do you know there's no theta?
If I am given a polar point and I want to switch to x and y, I am going to use the formulas x equals r cosine theta and y equals r sine theta. So this is almost like parametric, where theta is our t instead of the t, right? So in this case, my x is going to be equal to the r times the cosine at 2 pi over 3, which I know from where?
Your chart.
My chart. The cosine at 2 pi over 3 is going to be what number?
-1.
-1/2. Which then gives me what for my x coordinate? -2. My y is going to be equal to 4 times the sine at 2 pi over 3. Which happens to be what number? Root 3 over 2. This one doesn't turn out quite as nicely because I can't cancel the root, but it does give me 2 root 3. So the corresponding xy coordinate here is -2 up 2 root 3. It should make sense if you thought about how to graph both of these. If I graphed the polar point 4 comma 2 pi over 3, I'm going to rotate to 2 pi over 3 and go out 4. That puts me in the second quadrant. The xy that I just got back out is a -x, +y. Also puts me in the second quadrant. They should match up. If they don't, you missed a negative somewhere. Okay? Think about that. Now, if I want to change a polar equation into a rectangular format, I can use the same formulas. The only issue with this is it's not set up exactly like an r cosine theta or an r sine theta. I see a cosecant. Well, what do I know about cosecant? It is the same as 1 over sine. So can I keep manipulating this till it looks like one of those formulas above? I can multiply my sine over here, yes? If I do that, it becomes r times sine of theta is equal to 3. Well, according to those same equations I just used above, what is r sine theta the same as?
1.
Y. What is y equals 3? What kind of graph is that? A line. Guess what? This is the same thing, but in polar. So a horizontal line in polar looks like that. Can you guess what a vertical line might look like then?
No, I can't.
R equals 3 what?
Secant.
Secant. Yep. Would work that way too. Okay? All right. So our final things we're going to talk about today is how to graph some basic polar equations. You know when we do parent functions in x's and y's, like we just got to the place that if I gave you a quadratic in a certain form, you know enough about a quadratic to be able to just draw a graph of it. That's where we need to get with some of these polar ones. And I get that I'm going to throw a lot at you with these today. There's a lot of polar graphs, and we took like 3 years to learn our parent functions for like algebra stuff, right? We started in algebra 1 when we learned about lines and quadratics, and then in algebra 2 they added a ton of them, and then pre-calc I added a few more. We have like a day to talk about all the parent functions for polar. Here we are, okay? If you are given a graph, this is just kind of our quick breakdown of some polar common graphs, okay? R equals C, we've already talked about what this looks like. We said R equals 3 was a circle with radius of 3, right? So this one, if you see R equals a number, the center of this circle is always going to be 0, 0, and your radius is going to be C, whatever that happens to be. So if you see R equals a number, you graph yourself a circle with a radius of whatever that happens to be in the middle. That is not the only type of circle that you will see, though. There's a couple formats you will see for circles. One of them is this. One of them is what you see below. R equals a sine of theta. This is a circle on the y-axis somewhere. I know it's on the y-axis because it is a sine. Sine, according to those formulas above, back up here, is associated with y. See this? Y equals r sine theta, x equals r cosine theta. You are going to learn in polar graphs, when you have something associated with sine, it is typically centered somewhere on the y-axis. When it's associated with cosine, it is typically centered somewhere on the x-axis. Now, if you throw both of them in there, we're going to be seeing some different stuff, right? But we're looking for basics right now. Your center of this circle is going to be 0, comma, a over 2. So whatever that number out front is, it's going to help you find the center. The diameter of the circle is going to be A. So I'm going to give you two different examples here to draw. If you had R equals 2 sine of theta. Well, yeah. So the diameter is A, and it does go out from the center. The center of it will be at 1, because it's always half of that 2. So 0, 1. Honestly, if it's a positive 2 out front, I draw a circle on the y-axis with a diameter of 2. I don't even worry about the center. There's my circle, diameter of 2. It goes from the origin out and up, like you see mine. Now my circle is terrible there. Let's try again.
Why'd you write R equals 2 sine theta?
I just made that up, for example. How would it change if it was R equals, let me do another color here, R equals negative 2 sine theta? It's just on the negative y-axis, right? So my circle would start at the origin and go down to a diameter of negative 2. Right. So on this one, this would be a circle on the x-axis. The center will be A over 2, 0. The diameter will be A. So an example for this one. For example, if I gave you R equals 3 cosine theta. Again, I don't worry so much about the center. I started at 0. I go out a diameter of 3 on the positive x-axis. So I would say my circle looks something like that. Or I could give you R equals negative 4 cosine theta. Because it's negative, where do I draw it? The other way, with a diameter of 4. Okay. Mine look not circular. There, better. Those are the 3 forms you will see for circles. Circles are a must for you to be able to graph those on your own. You do not need a calculator for that. You do not need to plug in random like theta values and find points. That would just be stupid. Okay? Graph those on your own. Okay? All right. Flipping the page. Couple other basics. Theta equals an angle. If you have a theta equals an angle formula, This is a diagonal line through the pole. Okay? The pole is the origin. Okay? So, for example, if you had theta equals pi over 6, you would draw a diagonal line that is about where pi over 6 is in the unit circle. I would say, I know that's in the first quadrant, it's about this much. You do it forwards and backwards. Okay? This is kind of like your y equals mx plus b things, except there will be no plus b. There's no way to kind of move it up and down. It always goes through the pole. Nope. All right. We've already briefly talked about 5 and 6. In 5, cosecant is the reciprocal of what? Sine. So this one's associated with sine, whether you see it or not. Sine is associated with x or y? Y. This is a horizontal line at y equals a, whatever that a value is. So because secant is associated with cosine, what kind of line do you think 6 is? Vertical line at x equals a. So for example, if I gave you r equals 2 cosecant theta, you would recognize that as a horizontal line at 2. If I gave you a equals secant theta, so maybe r equals -3 secant, that's the same as a vertical line where? -3. There are 2 forms that you will see for rose curves. The rose curves are the flower ones with the petals, okay? You will see that version with a sine, and you will also see that version with a cosine. They change the orientation of the rose curve, and we're going to see what that looks like. In both of them, A tells the length of the petals. And yes, we call them petals, like literally petals of a flower. Okay? So this is going to be how far the petal goes out. That's going to be somewhat difficult on like a grid like this to think. You're going to almost have to think in like circles. Now that doesn't have to be crazy accurate, but we'll look at that, okay? In the sine version, in both of them, n tells us the number of petals. However, there is a key difference between different types of n. So in both of these, if n is even, there are 2n petals. If n is odd, there are just n petals. So in other words, if n is an even number, you are going to double it for the number of petals. If n is an odd number, it remains the same.
The one's even more petals.
Yes.
Can n be a fraction?
No.
That was so bad, Riley.
N is not going to be a fraction.
That was so bad.
Like, it's not.
And yet it might stick in your mind for later. You never know.
What if it-
I know, I heard. But it could. It could. Even more petals. There you go. All right.
My dad was a joke.
All right. And then other things. One more thing about this before we do some examples of them.
No.
Sine. If it is a sine rose curve, it starts in quadrant 1. Okay, and I'll explain what that means in a minute. If it is a rose curve with a cosine, it starts on the x-axis. Okay. Tangent? No. We do not see tangent polar curves. All right. So I'm going to give you a couple examples of these, an even and an odd, kind of to look at some different ones and how you might be able to graph these decently well by hand. There is no way that you're making these super accurate. Sometimes you just need to be able to see what it looks like, to see what's inside and what's outside of the two curves so that you can find the areas. Okay, this is not necessarily lots of accuracy. So, for example, R equals 3 sine 2 theta. The first thing that you do is establish, I know the length of the petals outward is 3, and I know how many petals does this have? 4. This is still circular. So you are going to think to yourself, I need to kind of evenly fit 4 petals in this graph, okay? So when I do this, I know it's a sine graph, which means it starts in quadrant 1. So that does not mean one of the petals is centered over the x-axis the way it would as if it was a cosine, okay? So if I have 4 petals to fit evenly on this graph, how is it going to fit? Well, isn't that just 1 in each quadrant? Yeah? And they're going to go about out to 3. Now, about out to 3 is kind of this circular, like, here's 3. Do you need to draw that in? No. But when you graph these, I am graphing a petal here, a petal here, a petal here, and a petal here, all about out to 4. That is what that graph would look like. 3, excuse me. 4 petals out to 3. You do not have to draw that, but that's how I kind of estimate how far out these go, because they're not out on the x-axis, right? So I can't exactly like say it's out to a certain distance, right? You will get better at these as you go. These come up a lot. They're kind of fun. All right. A secondary example for this would be R equals 3 sine 3 theta. What's the only thing I've changed? Okay, I've changed the n. So because the n is now an odd number, how many petals does this have? 3. So now think about it though. If I fit 3 petals in 0 to 360 degrees, think about how, like, where they're going to be positioned. It's going to go evenly. You're going to rotate kind of the same amount of degrees for each. So really, where do you think the first one is going to kind of be headed out towards? The first one's going to be headed out towards like around 60-ish degrees. Actually, not so much. How about this? Okay, I'm terrible at drawing these, just so you know. Terrible.
So is that like the input of it would be on like that
Here is how I know.
5/6 line?
Okay, you want to know how I know on this one? I know that they're going to hit their furthest point out when the sine is equal to 1, yes? Because the biggest that sine can ever be is 1. So the end of these petals is going to happen where sine is 1, right? So think about it. Sine is going to be 1 when 3 theta is equal to what radian? Pi over 2, right? Because sine is equal to 1 at pi over 2, right? So if 3 theta equals pi over 2, what does theta equal? Pi over 6. So I'm going to aim the end of the first petal at about out to pi over 6. Okay? And then I'm going to go evenly from there.
Wait, how does it go?
I'm going to keep these other two as similar to the previous two as I can so that you can see the differences. We're going to keep the A is 3, the length of the petals is 3. Cosine of 2 theta, this means how many petals do I have? 4, double. Now cosines, it says starts on the x-axis. That means your first petal is centered on the x-axis, the positive x-axis. So the first one is going to go out 3 here. And if, again, I have to divide 4 petals evenly, really what's that going to mean about all 4 of these petals? All centered on an axis. Okay. Wow, that's really bad. So because these do not start in a quadrant, we end up looking like that. Okay?
It's something for sure.
Mm-hmm.
The right side is really easy.
All right, so our difference on this one is what? It's odd. So how many petals do I have? 3. The first one is still centered on the x-axis. So that means the first one, 1, 2, 3. Can I count 3? I think I can. First one's here. Okay, so if we just kind of make them where they all 3 fit within this, where's my second one going to kind of head off to? Mm-hmm. It's about 2 pi over 3, really. It's kind of headed that way. And the other one is at like 4 pi over 3-ish. Okay?
Are we done?
Now, why would it be the pi over 3s? Just think about the number there.
Divided by 3.
Yeah, if I put in the 2 pi over 3 here, that would be cosine of 2 pi.
Oh.
If I put the 4 pi over 3 in there, it would be cosine of 4 pi. All of those are going to have a cosine value of 1, right? Same kind of thing back here. If I want the sine to work out to pi over 2, I have to think, what do I plug in for theta that would give me those? Well, those would be the 6th. 3 pi over 6 works out to pi over 2. If I plug in 5 pi over 6, that would be like 15 pi over 6 or another variant of pi over 2.
If it's even enough, should be fine.
Yeah. All right, the last types that we're going to talk about are the limacons.
I'm a Colin.
Okay?
Yeah.
Now this,
That looks like lemon to me.
if you actually look this up online, it has one of these little accents on the C. Okay?
I was literally about to write.
Yes. That is French. Okay? That is what says limaçon. If you pronounce this, it's literally limaçon. Like that. Limaçon. All right.
You will hear us well.
All right, so sine is still going to tell me that this is going to be centered on the y-axis versus the x-axis for these ones. Okay? So that will help us. The differences in these different versions are going to be the difference between A and B. Okay? So in question 9, our example is going to be R equals 1 plus 2 sine theta. Okay? In this version, your absolute value of A is less than your absolute value of B. Okay? These ones are less likely for you to be able to remember all the different versions. I will be honest. Okay? How you graph these is this. If you take your absolute value of A plus your absolute value of B, this is how far out it goes. These ones have what is called an inner loop. And the distance of the inner loop is going to be the absolute value of B minus the absolute value of A. Okay?
These mathematicians are.
A is going to give you the distance side to side. Okay? So if I take in this problem that I just gave you, absolute value of A plus absolute value of B, what's the furthest distance this goes out? 3. So I know it's all positive here, which means this is going to be centered on the positive y-axis because of sine. It's going to go out 1, 2, 3. That's the furthest it's going to go out because that's the absolute value of A plus the absolute value of B. The inner loop, absolute value of B minus absolute value of A, is going to give me what? 1. That's going to be as far as that goes on the inner loop. And then the side to side on the x-axis comes from the value of A. What's the value of A? 1. So it goes out side to side 1. Okay? When you play connect the dots, these always start at the origin. So before you play connect the dots on your paper, watch me do mine. I'm going to start at the origin. It loops through this, out here, back through this, into the origin, makes the inner loop, and finishes. Okay? It starts at the origin, goes through the x, through the farthest point, through the other x, back, makes the inner loop, and comes back. Okay? An alternate version of this would be r equals 1 minus 2 sine theta. What's the only difference I made on that one? It's got a negative b on that second term, which means it's the exact same shape but centered on the negative y-axis. So if I graphed that one, it would go through here, out, back, around, loop, but be on the negative y. On this next one, on 10, what's the only difference here? It's a cosine, so it's centered on the what? Huh? X. So a version of this could be 1 plus 3 cosine theta. This gets faster. So I know now the 1 gives me the side to side. The 1 plus 3 gives me the furthest out. The 3 minus 1 gives me the smallest loop out. So I know the 1 plus 3 means it goes all the way out to 4. I know the 3 minus 1 means the inner loop goes out to 2. And what does the 1 tell me? The side to side. So now this is on the y-axis, right? So when I play connect the dots on this one, it goes from the origin, out, around, back through here, inner loop, back. If I made that a negative 3, it just means it's centered on the negative x-axis. It would still go out to the negative 4 and out to the negative 2. It would go out, around, back through, inner loop, back. Okay? Now, that's as far as we're going to make it today.